All right. Now, this seems kind of out of order to me, but this is how we would calculate the least square regression line by hand. Okay, remember, as we're going through these videos, there's a lot of stuff really fast. So you might want to hit pause, get out your guided notes. You're going to find pretty much everything you need as we go through this video. So use the video as you see best fit. What works best for you? Okay. Probably lots of pausing and going back and checking it out. Okay. So let's take a look at this. This important fact: every regression line passes through the point X bar, Y bar. By definition, by the way the regression line is constructed, it will always go through the point X bar, Y bar. So no matter what, we always know one point on every regression line, the mean of X and the mean of Y, always. Okay, so we know that the equation of the prediction line, Y hat equals B sub 0 plus B sub 1 times X, where B sub 1 is the slope. And you can see the formula for the slope is B sub 1 equals R over standard deviation of Y, standard deviation of X. So let's look at an example. What's probably going to happen is they're going to tell us that the mean of X is 10. The mean of Y is 8. The standard deviation of X is 5, and the standard deviation of Y is 4. Okay, so let's calculate the slope from here. We don't even know any of the data points. We just have some of the variable or some of the values of the variables. We know what the means and standard deviations are, and we know that R is, let's say, 0.9. So how are we going to calculate the slope? Well, we have this formula here for B1. Okay. The slope is equal to R times the standard deviation of Y divided by the standard deviation of X. So B equals 0.72. That's our slope, 0.72. Now, how are we going to find the y-intercept to put this all together? Well, we know this equation up here, y hat equals B sub 0 plus B sub 1 times X, where if I know this fact here, every regression line passes through the point X bar, Y bar. I know a point on the line. So I'm simply going to plug in the slope and plug in the point that I know. So Y, 8, equals, I don't know the y-intercept, plus the slope times X. Since every single regression line passes through the point X bar, Y bar, then I have a point for X and Y to plug in. I'm simply going to do my math. Y equals B sub 0 plus 7.2. Subtract 7.2 from each side, and I find that my intercept equals 0.8. Now I've just calculated the least square regression line by hand. So for this example here, my least square regression line is y hat equals 0.8 excuse me, plus 0.72 times X. Probably won't be asked to do this by hand very often, but I think it's really good to know where does this equation come from and what are we actually doing instead of just pushing buttons in the calculator. All right. So finally, what are we going to do with these unusual points? Remember, we want to talk form, direction, strength. Anything unusual? Form, direction, strength. Weird stuff? Form, direction, strength. Unusual? So here is a regression line accompanied with its residual plot. Okay, they took the age at which you spoke your first word as the explanatory variable and your intelligence as your response variable. So what they were trying to do was predict, if we know what age you were when you first spoke, can we predict your IQ later in life? Okay. And you notice that there is a couple of unusual points. Child 19 and child 18 are unusual. What do we mean by unusual? We're not saying that this is a weird kid. We're just saying that the data points don't fit the rest of the data. They're different. They're unusual. They're outliers, as we talked about in Unit 1. Okay? We can have an outlier in the X direction, which would be child 18, because he doesn't fit with the rest of these values in the X direction. Or we can have an outlier in the Y direction, like child 19. He doesn't fit the rest of the data in the Y direction. Okay? So these are called outliers, regression outliers, or high leverage points. High leverage points is referring to the fact that these points here will have a lot of leverage, or they'll have a lot of pull on the regression line. For example, if we were to remove child 18, the regression line would become much less steep and it would decrease the y-intercept. Okay? If we were to remove child 19, it would also affect the direction. I shouldn't say the direction. It would also affect the regression line. It would make it more steep and give a higher y-intercept. Yeah, that's not very good. Anyway, child 18, extreme X value. He's an outlier, or he's a high leverage point. He affects the correlation and the slope and the intercept. Child 19, regression outlier or high leverage point, will affect the slope, the correlation, and the y-intercept. Okay? Now, when we make a residual plot of this data, we can see that child 19 has a huge residual relative to everybody else. Child 18's residual is quite small, but is very extreme on the x-axis. Okay? So we could have a high leverage point or a regression outlier in the y direction, such as child 19, or the x direction, such as child 18. High leverage points because they change the equation, they change the correlation. And this also is talking about here something we haven't referred to before. What if two data points have the same value? How would we show that? So they would use a different color or a different symbol. In this case, they've shown that these two purple points here represent there were two individuals with the exact same value. So it's just telling us, how do you put two dots on the graph if they're in the same location? Well, we're going to deal with that by using a different color, or sometimes you'll see they'll use a different symbol. They'll put like triangles instead of circles to represent that that dot there or that point there is representing two data points rather than one.